So I'm going to be talking about some work that we've been doing on building smart contracts to be secure by construction, and particularly looking at how to deal with reentrancy vulnerabilities, which have been a big problem, as you know. So I think one of the reasons why we have so much trouble with smart contracts is that the programming models that people have developed over decades were not really designed for the kind of environment that smart contracts live in. So smart contracts are being used to manage a lot of value, but the abstractions that we use for building programs, the kinds of things that are taught in CS 100 for appropriate values of 100, are this very friendly environment where you're not dealing with adversarial code, whereas the world the smart contracts live in is much more adversarial. You have trust boundaries that are being crossed by users, code, data, and of course the adversaries get to extract money directly when they're successful. So they're very strongly incentivized to find the bugs in your code in a way that they weren't in CS 100. So of course, there's been a lot of interest in developing tools for finding vulnerabilities in smart contracts. And I think a fundamental weakness of most of these efforts is that they're looking at contracts in a kind of one contract at a time. And actually, a lot of the vulnerabilities that we've seen, these high-profile problems, have been because of interactions between contracts. So even going back to the DAO, you had an interaction between the DAO and user contracts involving reentrancy. The parity wallet vulnerability, again, there was an interaction between two contracts, and even the recent Uniswap vulnerabilities. This involves actually 3 contracts interacting with each other. And so I think as we see the smart contract ecosystem developing, we can expect to see more and more complex interactions between more contracts being exploited. And so what we need to, I think, do is rethink how we're building contracts and come up with ways to build contracts that give us stronger guarantees of security against kind of arbitrary interaction between different contracts. So this is a kind of compositional security. So how do we get compositional security is sort of the fundamental question. And I would argue that the way to do it is to start with information flow. So on the blockchain, the main concern is the integrity of information. Of course, confidentiality is another issue, and I'm not going to talk about it, but it can also be addressed through information flow reasoning. So of course, the problem is that adversaries are providing some of the things that are controlling your computation, some of the information, some of the computation itself. And so the insight is that we can think about controlling how adversaries influence data and computation by controlling information flow. So we want to control the flows of information from untrustworthy sources of information to destinations that should be more trustworthy. And the nice thing about this perspective on computer security is that it is kind of fundamentally compositional. Information flow is talking about an end-to-end constraint on how the system behaves. And so as a result, when you put 2 different things together, whether they're smart contracts or even just functions making up a smart contract, then and the things you're putting together already obey the rules on secure information flow, then when you plug them together, then with some caveats, like the fact that they should agree with each other at the boundary where they're being composed, then you expect to get a secure, larger system. So here's an example of some code from a programming language that we've been developing for smart contracts that we're calling SCIF, stands for Smart Contract Information Flow. So this is a language in which which looks kind of like other smart contract programming languages, but the compiler is going to check ahead of time that the information flows that arise in the code are secure. So here is how we might start to write code for a simple wallet contract, which you can think of as being sort of similar to a core piece of the DAO. So So here we have a set of balances, which are a map from addresses to the balances of different users. And then there are functions withdraw and deposit that allow us to withdraw and deposit money. So what you'll notice here is that there's some stuff highlighted in blue that you would not normally expect to see. In particular, the balances storage variable has this annotation in braces that says this. Now, in this case, the word this stands for this current contract. And so what this is saying is that the balances are as trusted as the contract itself. So this would be actually the default annotation. We don't actually really have to write that annotation down. But if we want to have something that is at a different level of trust than the current contract, we can express it explicitly. So for example, we could write something more exciting than this, like identifying the name of some other contract. And different contracts can actually express trust in each other, although I'm not showing that. There's a withdraw method, and since this is labeled, annotated as public, then its default annotation is that it's untrusted, which I'm writing as an underscore. That kind of represents anybody on the blockchain. And the parameter amount is also untrusted. So in order to allow the amount to affect the balances of the of users, we have to explicitly say that we have done some sanitization of that untrusted variable. So that's what this endorse thing is doing. So endorse is a kind of statement which is functioning as a kind of typecast at the information flow level. And what it's saying is we're going to endorse amount from being something that's really not trusted at all to being trusted by this contract if the condition, the if condition holds. So this is what we call a checked endorse. Okay, and so that's the way we could write this code. And so the compiler will check the information flows. Now there's actually a vulnerability in this code that you might have noticed if you've thought about these reentrancy vulnerabilities in the past. And so in fact, if you write this code right now, our compiler will still not quite accept this. And to talk about that, let's talk about reentrancy. So we have been working on information flow for a long time. And what we realized when we started looking at smart contract vulnerabilities was that the existing rules for checking secure information flow weren't capturing these reentrancy vulnerabilities. So these are cases where we have information flowing back and forth between two or more contracts in a pattern that allows the security to be violated. So let's look at how reentrancy breaks things in a little bit more detail and see how, through the lens of information flow, we can understand what's happening. So we have some kind of automated bank like that contract that I was just showing you, and it has a set of balances. And now we have a user, Bob, who comes along and says, send me some money. So he's calling that withdraw function that I showed you. And so what the code I showed you did was it checked the balance, it sent money back to Bob, and then waited for Bob to return, and then decrease the balance. Okay, so now as you may be, as you know, probably, there's an attack here where Bob can say, well, I'm gonna send the money, and when he gets the money, rather than immediately returning, he issues another call in to ask for more money. And since his balance has not been decremented yet, you can get more money. And so we can get a whole series of calls happening in which Bob extracts lots and lots of money. Okay, so this is in fact kind of the core problem with the DAO. And so this is a case of reentrancy. Okay, so what's going on here from the perspective of information flow? We have some trusted balances, which I showed you in the code. And then we had a bunch of code running inside a method that really needed to be a trusted method in order to do those operations where it was updating the balances. So what's happening from the perspective of information flow is that Bob is an untrusted source of information. He's making a request. He calls into withdraw, which is trusted. and then withdraw returns to Bob. And then Bob makes another call, that reentrant call, calling back into trusted code. And so that pattern there, where we went from trusted code into untrusted code and then came back into trusted code, is the essence of the vulnerability. That's the reentrancy that we're worried about. And by looking at it from this perspective of trust levels, we can see more clearly what's going on than when we just think about it as control flow among contracts. So what we've realized is that the right way to define insecure reentrancy is as something we call L reentrancy. So L here stands for a level of trust in our various levels of trust. You can think of L here as just the name of a contract. So if we have an execution stack where we have two computations trusted at level L, but they're separated in the stack by an untrusted contract, then we have L reentrancy. So here's that picture that I showed you before, where we're thinking about the level of trust of the contract as, say, T, and when we have that pattern where we go from T into untrusted code and then back into T-level code, we have T reentrant execution. And the problem is that that might violate the invariance of the contract at level T, like, for example, invariance relating the balances in the contract. So the thing to notice here is that this definition is not based on the boundaries between contracts, but instead on integrity levels. And so what that means is that we could have a pattern where we have two contracts which are both at one integrity level, perhaps because they trust each other. And that would be, and even though we have a flow of control here that's going from T into untrusted code and back into T, which we would consider to be a T reentrant, and indeed can be exploited to create reentrancy-based vulnerabilities. So we would consider that reentrant at integrity level T, but it's not what we call object reentrant, which is the kind of notion that most people have previously used for defining reentrancy. At the same time, we can have a case where there's a contract which has information at different levels of integrity. Some information is at the level T, some is at a lower level of integrity, and this flow of control we would not consider to be T reentrant, because it actually doesn't admit these kinds of reentrancy attacks, but conventional notions of reentrancy would have considered this to be reentrant. So this satisfies what we are calling object reentrancy. So, and in fact, there are cases where you would like to do this kind of computation. You would like to allow this, to allow contracts to be as expressive as possible without violating security, and yet some of the existing mechanisms that people have proposed for blocking reentrancy would rule out this kind of code, even though it's not necessarily a security vulnerability. Okay, so from the information flow view, then what's going on here, really? What reentrancy attacks are doing is they're exploiting something that we call downgrading. Downgrading is any case where you have information that is being allowed to flow in a way that's not immediately obviously secure from the standpoint of the information flow security policy. So in particular, anytime you have untrusted information flowing to trusted information in a system, that's a case of downgrading. It's called endorsement. So if you endorse information that is untrusted, you're now treating it as more trusted than it might appear to be on the surface. And so from the information flow control view, when you enter trusted code based on the call from an untrusted caller, what you're doing is endorsing the control flow of the application. So you're taking untrusted control flow and treating it as something that is now trusted. So this is known, I was showing you earlier that we can label variables in the contract with integrity labels. There's also a hidden label here, which we call the program counter label, or PC label, which is capturing the integrity of the control flow. And so in that T reentrant execution, what was happening was we had two endorses. We had an endorse of the program counter to T, and then there was another nested endorse inside the scope of the original endorse. And that's the problem. That second endorse is the thing that we need to prevent. So, so these reentrant attacks are exploiting the endorsement, the downgrading of integrity. Okay, so that insight gives us then a mechanism for solving the problem. So in our recent Oakland paper, we defined a notion of what it means to be secure against reentrancy. So that the effects that are possible with reentrancy should also be possible without it. So the reentrancy doesn't give adversaries any additional power. So what that says is that if you have a T reentrant execution, lowercase t, then we should be able to come up with an equivalent execution T prime that has the same bad effects, but does not have any T reentrancy in it. And if we have that, then what that's telling us is that these nice compositionality properties that I was telling you we got from information flow control are still going to hold, even in the presence of potential reentrancy. Okay, so the way that we do this is that we introduce a locking mechanism. And the locking mechanism actually can be either a static locking mechanism that's enforced by the compiler or a dynamic locking mechanism that is enforced at runtime with some cost but additional flexibility. So we lock integrity. We think of this not as locking. Some people have proposed we should be able to lock contracts, but we're going to be locking integrity levels instead. So whenever we endorse control flow, what that means is we need to lock the corresponding integrity level. And then we're going to prohibit any future endorsements to that integrity level. Okay, so when we go from, in our example program, we go from untrusted to trusted and we call withdraw. Withdraw was a method that was endorsing the program counter. It was endorsing us up to the trusted level. And at that point, we lock that level of integrity. And then that's going to prevent us from doing another call. So when we want to do an endorse, we have to satisfy an equation, which I guess I won't explain in any real detail. You can think of this as being kind of a set notation. What we're saying is that the program counter, the original program counter, the from location, needs to be a subset of the union of the new program counter with the set of locked integrity levels or locked contracts. There's a more general way of thinking about it mathematically, which is why these things are square union and a square less than or equal. So it's actually a lattice. Okay, so then given that, when we come back to do the second, when we want to do a withdraw, that's perfectly fine. When we have that second withdraw, the one that caused the reentrancy problem, that's going to run into the lock and it will be prevented. And in fact, we can show that this rule then provably enforces that notion of reentrancy security that I defined on the previous slide. Okay, so we allow the good stuff, we prevent the bad stuff. So now I'll just show you what the code actually looks like. So I showed you this code earlier and I said it almost type checks, but in fact, what happens is that the compiler says, no, I'm sorry, I can't allow this because the control flow integrity is going to be low after this call to send. And so the assignment to a high integrity variable balances is going to be prevented. Compiler doesn't allow you to do this. So one way to solve this problem is to acquire a lock around the call to send. And that dynamic lock will restore our integrity level after the call to send. After the lock, the integrity level gets restored to high integrity. And so we are able to prevent the reentrancy. We can also fix this by reordering things so that the send happens after the update to the balances. So now all of the high integrity effects are happening before send is called. And so we don't have to acquire a lock, and the compiler will also tell us that this code is perfectly fine as well. So we're able to handle both of these kind of natural solutions to the original vulnerability. And in fact, other examples that I mentioned, like Uniswap, can be handled, as well as more exciting contracts that use reentrancy in a productive way like, for example, the town crier contract that Ari Jules and others worked on, which has some useful reentrancy in it. We can type check it securely. One thing to notice, one other change that happens here is that we have, if we want to use this solution that I just showed you where we reordered the code, you'll notice that with the withdraw function itself now is kind of just as dangerous as the original send. And so we'll have to change the label to withdraw to reflect that, to prevent further reentrancy attacks from being done using withdraw. So we can capture that aspect of the contract between the caller and the callee precisely as well. Okay, so to wrap up here, what I've been showing you is that we can enforce integrity in a compositional way in smart contracts, and information flow is a really nice way of thinking about how to enforce security compositionally. And then I showed you, well, actually, the conventional information flow control stuff that's been people have been working on since the late 70s doesn't quite work for smart contracts because of reentrancy. And what we showed in our Oakland paper is that nevertheless, we can use information flow integrity to think about reentrancy in a more precise way. We can define what reentrancy is better in this way. And then that also gives us a mechanism for restoring that nice compositionality so that we can now more freely combine different contracts together and other kinds of software. This actually works beyond smart contracts. So we can get a locking mechanism that provably enforces the right definition of reentrancy. And in fact, we have a language that's in progress that I've shown you some snippets from that implements the mechanisms that I've been talking about. Okay, so with that, I'm happy to take any questions that we have time for.
Thanks very much, Andrew. Any questions from the audience? Feel free to unmute yourself or to provide your questions via chat. Okay, then I guess we'll end there. Thanks again, Andrew.
Thank you.
This was the last talk of the session and the day. And oh, sorry, go ahead.
Just wanted to mention that Ethan Cicchetti, Sichu Yao, and Haobin Ni did all the work on this. So it is a recognition. Okay, thanks.
Okay, thank you.